In the Netherlands, there's an ambitious company that builds one of the most advanced and expensive tools in the world. A single unit costs hundreds of millions of dollars. When companies buy one, they also need 250 engineers to install the 165-ton device in a process that typically takes half a year. But despite this steep cost in time and money, many microchip makers desperately want one of these machines. The $100 million question is why. The answer had to do with something called Moore's Law, first coined by Intel co-founder Gordon Moore. This law says that every 1 to 2 years, the number of transistors can fit on a given size computing chip will double. By extension, the rough number of calculations the chip can do per second will also double. Now this law isn't the physical law like gravity. It's just a trend more observed during the early 1960s. But the chip maker turned the trend into goal, and in turn, consumers learned to expect computing progress to continue at this exponentially fast pace. And the amazing thing is, for 6 decades, it pretty much has. Thanks to Moore's law, chips have gotten smaller, faster, more efficient, and cheaper. But today, there are four key problems that trip up this trend, potentially ending Moore's law and fundamentally changing how we make progress in computing. The first is transistor size. Transistors are basically on-off switches, and these building blocks of digital computing have been shrinking since the 1960s. But recently, they've gotten so small quantum physics has begun to interfere with their functions. When the transistor switch or gate is less than 20 nanometers, electrons will turn along it continuously, turning a crisp on-off switch into a hazy dimmer. The second problem is heat. Chip makers make components smaller and more complex. The copper line that run between them need to be thinner and longer. This increases their electrical resistance and results high heat that impair chip performance that can't be easily dissipated. Today, chip can already run hot enough to cook an egg, and temperatures are only predicted to increase without new innovations. While both these While both these issues represent limits in the fundamental physics of chip making, researchers haven't stopped trying to solve them. Unfortunately, their solution often exacerbates the third major problem, chip makers' environmental impact. For example, swapping copper lines for ruthenium could help pack transistors more tightly and keep chips smaller. But that metal is far scarcer than copper, would require new mining infrastructure. Similarly, the technology currently used to make today's smallest transistors requires huge amount of energy and chemicals called Pathora and Polythora substances, which can take thousands of years to break down in the environment. Managing these first three problems contribute to the final issue, cost. To keep achieving Moore's law, chip makers have to make individual chip components smaller. But this is where the costly $400 million machine comes in. This marvel chip-making science shoots the stream of tin droplets into a vacuum chamber before blasting them with high-energy laser that vaporizes the tin to create plasma. In turn, the plasma emits a 30.5 nanometer wavelengths of ultraviolet light that can be used to produce incredibly small transistors. This remarkable feat of engineering has helped chip makers keep up with Moore's law. But a chip keep getting denser, intricate manufacturing plants keep getting more expensive. This trend has been so consistent, it's actually earned the nickname Moore's second law. Obviously, all these trajectories are unsustainable. Manufacturing plants can't keep increasing in price. Our ecosystem can't endure endless mining and pollution, and the laws of physics are unlikely to change anytime soon. Fortunately, Moore's law is flexible, and there's no reason we can't introduce new goals to keep making computing progress responsibly. Perhaps we could introduce a new sustainability law. Smaller transistors already use less material and produce less e-waste. And advancement in electric photonic integration, allowing chip to use less energy and generate less heat. So perhaps chips should be made twice as sustainable every several years. Whatever the answer is, we make the laws, so the future is up to us.